Nikita Murthy, Faculty of Information Science and Engineering, Maharaja Institute of Technology, Mysore. We were studying the topic Connection Oriented Transport TCP. We were studying the topic Connection Oriented Transport TCP. Today under this we are going to study reliable data transfer. Under this we are going to study a topic called reliable data transfer. Earlier we had seen how to provide a reliable data transfer over UDP, isn't it? Here we are going to study how to provide reliable data transfer in TCP. We already know TCP provides reliable data transfer. That means when a sender has sent a message to the receiver without the message getting corrupted, without any gaps in the message, without any manipulation or any reordering, whatever the message has been sent, it will be correctly received by the receiver. That will be ensured by the TCP. So, here now you are going to see how TCP provides reliable data transfer over unreliable IP protocol, because TCP is a transport layer protocol. It will be running in the transport layer. When the layer beneath that, that is in the network layer, IP protocol will be running, which is unreliable. Now, so even though IP is unreliable, TCP provides reliable data transfer. We will discuss how TCP provides reliable data transfer in two incremental steps. First, we are going to study a TCP sender, a description how TCP provides reliable data transfer. Here is the simplified version of the TCP sender. Here they have considered two variables, that is next sequence number. Next sequence number they have initialized to initial sequence number, and send base is equal to initial sequence number. Here next sequence number and send base both are initialized to initial sequence number. Here they are considering three events. Here they are considering three events. The first event is what happens when the TCP receives the data from the upper layer, and the second event is when the timeout occurs, when it is waiting for the acknowledgement, and when it does not receive the acknowledgement, what happens, what action has to be taken. And the third event is when it receives the positive acknowledgement. So, we will see what happens. Let us consider the first event when it receives the data from the above, that is data received from application above. That means when it receives the data, what we have to do? We have to create a packet, we have to make a segment, isn't it? It will create a TCP segment with the sequence number is equal to next sequence number. The sequence number, it will be equal to next sequence number, because the previous sequence number it is already been sent, isn't it? That is why we have to initialize the sequence number to next sequence number that we have to send. And then if the timer is not yet set, if the timer is not yet started, we have to start a timer. And then after starting the timer, we have to send the TCP segment to what? To network layer. From the transport layer, we have to push the data to the network layer. What protocol is running over there? IP. Then that means you have to send the data to IP. And then we are initializing next sequence number is equal to next sequence number plus length of the data. That means next sequence number, the next sequence number which has to be sent after this, that will be, we are incrementing it over here. What will be that? That will be equal to previous sequence number plus length of the data. If the previous sequence number is 90 and then the length of the data is 10, then the next sequence number would be 100, 90 plus 10. Next, consider next event when the timeout occurs. When the timeout occurs, what we have to do? If the timeout occurs, that means the packet that we have sent, it is not correctly received by the receiver. What we have to do? We have to retransmit the same packet, isn't it? That is what they have said. we have to retransmit not yet acknowledged segment with the smallest sequence number. That means the packet which has not been acknowledged, that packet we have to retransmit, and then after retransmit again we have to start a timer for that. Next consider the next event. What happens when we receive the acknowledgement? When we receive the acknowledgement, what we are going to do is, we have used one more variable called y, when y is greater than send base. Here send base is nothing but it is a sequence number of the oldest unacknowledged packet. Send base is the oldest unacknowledged packet, it is the sequence number of that. When y is greater than that, when the y is greater than that, we are assigning y to send base, and then if there are currently any not yet unacknowledgement segment, that means if there are still any unacknowledged segments, then we have to transmit them and we have to start a timer. That means if you have that means when we receive the acknowledgement, positive acknowledgement, that means the packet that has been sent, it is correctly received, we have to send another packet. That is what they are meaning it over here. Now let us try to consider a few interesting scenarios. While transmitting between the sender and the receiver, when the TCP is connected both of them, we will try to look at few scenarios. The first scenario is, so this is the first scenario. Here they have tried to connect two hosts. Host A is connected to host B through TCP. They have used TCP as the protocol as a communication channel. Now suppose host A is sending a packet with a sequence number 92. Host A is sending a packet with a sequence number 92, and what is the length of the data, how much data it is sending? 8 bytes of data it is sending it from host A to host B. What will be the acknowledgement number means? 92 plus 8. I said it in the last in the event itself. That means next sequence number is equal to next sequence number plus length of the data. That is what they have given it over here. The next sequence number would be previous sequence number plus length of the data. That is why acknowledgement 100 would be sent. That means it has received the sequence number packet 92 plus 8 bytes of data. That is why it is sending the acknowledgement of 100 with the sequence number 100. Now suppose this acknowledgement while traveling has lost. While traveling this packet has get lost, and the timeout has occurred. We have set a timer for this packet, and since we have not received the acknowledgement within the timeout has occurred. What happens? We are going to retransmit the packet again. So with the sequence number 92 and the same 8 bytes of data will be retransmitted to host B, and then it will send the same acknowledgement with the sequence number same 100. Now, let us consider the second scenario, second interesting scenario. Now, this is the second scenario. Here also host A and host B are connected through TCP. Now, here instead of sending one packet, here it is sending the multiple packets. As of now, it is sending 2 packets from host A to host B, 2 packets with the sequence number 92 and 8 bytes of data, and next sequence number is previous sequence number plus data, that is 100. That is why the next sequence number would be 100, and then 20 bytes of data is being sent. Due to some delay in the network, maybe because of some congestion or network flaw, the acknowledgement has not received within the time. The acknowledgement, here is the time interval, this is the time interval. Within this, the acknowledgement is not received, it is received after the timeout at this point of time. So, when we did not receive the acknowledgement within the time, what happens? For the sequence number 92, for the first packet which you have sent, for that the timeout has occurred. What we will do? Instead of sending both the packets, here the special scenario, this interesting part which you have to note is here that instead of sending both the packets, here it is sending only one packet, the earlier unacknowledged packet, it is sending only that packet to the host B. Now, here it is waiting, again it has set the timer, it has set the timer for the sequence number 92. And then what happens? Since host B has already received both of the packets correctly, what it will do? It will not acknowledge the previous for the previous packet, it will acknowledge for the recent packet it has received, it will acknowledge the recent packet it has correctly received. That is why it is sending the acknowledgement of 120. It is sending the acknowledgement of the 120 that was, it was recently received, because it was already received and later it received the next sequence packet, and instead of sending the again acknowledgement with 100, it is sending acknowledgement with the sequence number 120. But these are the 2 points which you have to note. Here when the retransmission is happening, it is sending the oldest unacknowledged packet, only that packet it is retransmitting. We have to note 2 interesting points over here. When the retransmission is happening, it is sending the oldest unacknowledged packet, and since it has already host B has received that packet, it is going to acknowledge to the recent packet it has received, not the packet it has retransmitted, to the recent packet it has received. That is why it is sending the acknowledgement of the 120, that is 100 plus 120 for the recent packet it received. The next interesting scenario we will see now. This is the third interesting scenario which you can observe over here. Here also host A is connected to host B. Again host A is sending a packet with the sequence number 92 and 8 bytes of data it is sending, and it has correctly received by the host B, and it is sending the acknowledgement with sequence number 100. Here one thing you have to observe here, look at the timeout interval, it is very large. The timeout interval is very large. So, while it is waiting for the acknowledgement for the first packet, it has already sent the next packet. It has already sent the next packet with the sequence number 120 bytes of data. But the acknowledgement for the first packet, it is been lost. It was lost in the network. But the next packet which was sent, the acknowledgement for that was correctly received. But here it is not even though timeout has occurred and the acknowledgement was not received, the host A is not retransmitting the first packet. Can you guess why? The reason is that since it has already received the acknowledgement of the next packet, that means if it has not received the first packet, the host B will never send the acknowledgement with next recent packet. That means only if it has correctly received, then only it will send the acknowledgement of the recently received packet, isn't it? If it has not received this packet, the acknowledged number would be 100. That means here also it would have sent again 100. Here instead of 120, it would have sent again 100. That means it has not received the packet, or else if this was received and the previous packet was not received, it would have sent the acknowledgement of the recently received packet only, not the ones which was lost, and then if even though some packet is lost, the next packet which will arrive, it will not send. Let us look at it this way. I have considered few packets. This is the packet with 100, sequence number 110, 120, 130, and this has been sent between host A and host B. These are the packets which are being communicated between host A and host B. So, now suppose 100 was sent to B and it was correctly received. 100 was sent to B, it was correctly received, and the acknowledgement of what? Same 100 would be sent. The acknowledgement of 100 would be sent again. Now 120 was sent between host A to host B. 120 has sent between 110 was sent between host A and host B. Due to some congestion or some problem, this was not received by host B. This was not received by host B. the host B, what it will do? It will send the acknowledgement of the previous packet it was received, the recent packet it was received, it will send the acknowledgement of that only. And then before timeout, if it sends the 120 also, even though it was correctly received, since 110 was not received, here also it will send the sequence number of acknowledgement number of 100 only, since it has not received the packet of this, and even though it has received the recent packet also, since this was missing, it will send the sequence number of the previously correctly received, orderly correctly received packet only. So, when before timeout, when it receives the acknowledgement of this, the host A can aram se make out that 110 packet was not correctly received, have to retransmit that packet again. The same concept they have tried to explain it in a concept called fast retransmit. They have tried to explain the same concept under faster retransmit. That means, when host receiver is sending the acknowledgement with the same sequence number, since the packet was lost, what it will do? It will send the sequence number of the recently received packet, that means previously received packet, the oldest packet. What happens at the host A? The duplication of same acknowledgement number. As we saw earlier, 100 sequence number, 100 sequence number, same 3 packets with the acknowledgement sequence number 100 was received. That means duplication of acknowledgement number. Duplication of acknowledgement sequence number will help the sender to know that there was a packet which was missing, I have to retransmit that packet. So, with this we can within the timeout if we receive duplication of packet, that means if the sequence number 100 acknowledgement number 100 is received within the timeout, if these are happening within the timeout, the sender can aram se make out that the packet is missing, I have to retransmit the packet. So, with this the timeout interval we can keep it as small as possible, and within the timeout also we can retransmit the data. That is why the name faster retransmit. That means we can in the earlier stage only we can make out that the packet is missing, we have to retransmit the packet. Within the timeout all this action is happening. Let us try to look at that example. That is why they tried to show it in the diagram. Between host A and host B, multiple packets are being sent. First, a packet with the sequence number 92 and 8 bytes of data are being sent, and the acknowledgement number of 100 is being sent to the sender again. Now, sequence number 100 and the 20 bytes of data, this packet is lost in the network. This packet is lost in the network, and the next packet with sequence number 120 and 15 bytes of data, it has been received by the host B, but still it won't provide the acknowledgement number, the recent one. It will provide again which was recently correctly received, which was in order. That acknowledgement number only it is providing, acknowledgement number 100 only it is sending. When the sender receives the duplication of acknowledgements with the same sequence number, within the timeout can occur, the sender can make out that a sequence number of 100 is missing, 92 sequence number is correctly received, the sequence number 100 packet is lost, it is not received by the host B, I have to retransmit the same packet. So, within the timeout can occur, the retransmission is happening, that is why the name faster retransmit. The next topic which you are going to study is flow control. This is the very special feature which is provided by the TCP, that is flow control. It also provides one more, that is congestion control, which we will see it in the later sections. Now, we will see flow control. Flow control and congestion control are not same, both are different. Even though they are provided to keep up the capacity of the connection, both are not same. Flow control is about sending how much capacity the receiver is able to receive. If the receiver is able to receive 1 Mbps of data, if you are sending 1 Gbps of data, what happens? There will be overflow, the data will be overflowed and the correct amount of data will not be received by the receiver. We know if this is the sender and this is the receiver, if this is the sender and the receiver, the TCP will assign a buffer, isn't it? TCP will assign a buffer both at the sender and the receiver. You may ask, why we need to provide a buffer both at the sender and the receiver? Because TCP is a full duplex, because the sender can send a message to receiver, at the same time receiver can also send the message to the sender. That is why both at the sender and the receiver TCP is providing buffer. Now, the capacity of the receiver side buffer is only 1 Mbps. It is able to receive only 1 Mbps of data, or let us say 1 MB. Only 1 MB it is able to receive the data. If the sender has sent 1 GB of data, if the sender has sent 1 GB of data to the receiver and the buffer is able to hold only 1 MB of the data, what happens to the rest of the data? It will be dropped, it will be overflowed, there will be a loss of data, isn't it? That is why while sending the message we have to know how much the receiver is able to receive, isn't it? That is why we use a special segment in the TCP segment. You might have remember, we use a segment called receive window. We use a special segment in the TCP segment called receive window. Why do we use this? Because it is very necessary for us to know what is the receiving capacity of the receiver. That means how much data has to flow in the connection so that the data is not lost and the receiver is able to receive the data fully. To know what is the receiving capacity of the receiver, the TCP uses two special variables. TCP uses two special variables at the receiver side, that is last byte read and last byte received. So, these are the special variables the TCP uses at the receiver side to calculate the receive window of the receiver. Last byte read is the, it is the byte, it was the last byte which was read by the receiver from the buffer. It is the last byte which was read by the receiver from the receive buffer, and last byte received is the byte, it is the last byte which was received by the receive buffer. It was last received byte which was received and was stored it in the receive buffer. Let us try to look at that in a diagrammatic format. So, if this whole thing is a receive buffer, if this whole thing is a receive buffer of the receiver side, and the data is flowing from the lower layer, that is from the IP, and from here it is going into the application process. Now, suppose this whole thing is a buffer, only in this part the data is residing, and there is some spare room also, that means it has some more room to hold some data. That means if we look at those variables, what happens if this is the last byte read, if this is the last byte read, that means the application process has read this byte for the last, and this is the last byte received. And this is the last byte received. So, if we want to know what is the receive window, means the remaining spare room is the receive window, the remaining spare room is the receive window. So, how do we calculate the receive window, means how do we calculate how much the spare room is available, means what we have to do, the whole thing, the whole receive buffer minus what, last byte read minus last byte received. From this whole thing, if we remove the TCP data in buffer, we will be left out with what, receive window. We will see the formula for this. But if we, before we come up with the formula, we have to make sure that how much data is residing in the buffer, it should be always greater than or equal to what? A receive buffer. It should not exceed the buffer capacity, isn't it? How do we get to know that? The last byte received minus last byte read, that means this is the data in the receive buffer, isn't it? This should be always less than or equal to what? Receive buffer. That means we have to make sure that the data that is residing in the buffer, it should not exceed the capacity of the receive buffer. Now let us look at the how do we get to know the receive window of the receiver. Now if the receive window is equal to receive window is equal to receive buffer minus last byte received minus last byte read. That means the whole of a receive buffer, if we minus the data in the buffer from the whole of a buffer, what we will be left out? Our amount of spare room. That is what is a receive window. Now we have calculated the receive window. Now we have to also make sure that the sender is not sending a more amount, isn't it? To make sure that at the sender side, the TCP also keep tracks of two special variables called last byte sent and last byte acknowledged. At the sender side, the TCP keep tracks of the two special variables, last byte sent and the last byte acknowledged. That means this is the byte, this is the packet which was sent recently, and this is the packet, and this is the byte or the packet which was acknowledged. So the difference between them will give us what? The difference between them will give us the unacknowledged packets. So the difference between them will give us the unacknowledged packets. The making sure that the unacknowledged package does not grow above the receive window, we can make sure that the sender is not sending too much to the receive buffer. So by keeping track of the unacknowledged packets, the difference between these two variables, we can make sure that the sender is not sending much amount. That means last byte sent minus last byte acknowledged. That means total unacknowledged packet should be always less than or equal to receive window. What is, we should always keep it to the less than or equal to the receiving capacity of the receiver. With this we can provide a proper flow control between the sender and the receiver. With this, the flow control concept is finished. Thank you.